The following program is brought to you by Element 14, the electronics community where you can connect and collaborate with top engineers from around the world. Join now at element14.com/presents.
You're watching Element 14 Presents. My name is DJ, and I can stand on my own 2 feet. In fact, I can even stand on 1 foot. Now, I won't be offended if you're not impressed by that, because us bipedal mammals do that all the time. But we take it for granted, and it's actually a really challenging problem in robotics to get something to stay upright. And if you want to make a cool robot, you should learn before you walk, or roll before you accelerate quickly. I didn't really think that analogy through, but today I'm building a balancing robot, and I think it's time for us to get started.
Amazing hacks. Inspired designs. Each week, Element 14 Presents brings you innovative projects using electronics, engineering, and more.
So, what's the big idea? Well, the actual big idea is I want to build a very particular type of robot. See, I'm kind of a big fan of robots, and the particular type of robot I want to build is called a Securitron, which is a balancing monowheel robot from the Fallout franchise. And whenever I'm building something complicated, although I don't want to, the best thing to do is to focus on the hardest challenge of a design first. And for a monowheel balancing robot, the monowheelie balancing act, I think, is the hardest aspect of that robot's design. So I'm actually building a small-scale prototype that has no form or design that I like. It is purely functional, so I can learn the control fundamentals of a balancing robot. And that is the actual goal of the ultimate build, but today I'm just building a little guy that can stand upright. Now, one of the first things we want to do is measure the angle of the robot so we know whether or not it's falling over and can maintain balance. Normally, you'd have another processor as well as a separate sensor, and that is totally fine. But if you want something even more compact, I've decided to use the Arduino Nano 33 BLE, which incorporates a 9-axis inertial measurement unit. So we've got acceleration, gravity, magnetism, all in one handy package, as well as Wi-Fi and Bluetooth. This is just such a cool dev board, and I think it's going to be perfect for this build. So this will allow us to measure the pitch of our robot, as well as allow us to do some fun, perhaps a simple web page to control it. So this is going to be the heart of our build. All right, we are going to jump ahead to the future because I've made a mistake, and this compromises the whole design. Hooray, we've made a big mistake. So this right here is a voltage divider because I thought, hey, what if I want to measure the voltage of the battery, because these lithium-ion batteries have problems if they're over-discharged. So I want to keep tabs on that voltage. Perfectly logical thing to do. But what I didn't realize is that I'm careless. And the voltage divider I've got right here is a 10 kilo ohm and 5.6 kilo ohm resistor, which would be totally fine for measuring the voltage of a 2-cell or less lithium-ion battery. You can possibly predict what's going to happen, but so this is only good for a little over 8.4 volts. So at 8.4 volts, this should read at about 3 volts on the ADC, or one of the analog in pins of this board. Now, that sounds fine, but I also realized at some point, hold on one second, that I wanted more power. I'm like, oh, I've got a 12 volt DC motor. Why don't I just power it with 12 volts? But in my mind, I kept thinking, oh, I'm also just gonna use a 7.4 volt battery. I just couldn't keep it in my head that I was going to swap out to a higher voltage battery for the motor and somehow also have my lower voltage for the ADC. So I never even plugged this in and just set it aside. And this was attached to my circuit, which meant that I was always running roughly 4.5 volts across the ADC of the Nano. Now, no magic smoke, no magic smoke. It didn't die, and in fact, it still connects to my computer, but I started noticing that it would occasionally halt after a minute or two, which is not desirable behavior. So always double check that you're using the right battery, and don't be like me and don't compromise your entire project. So I can't trust that this Nano is going to work reliably, so it's gone. It's out of here. I'm moving on to a new design, and I just got to let it go. All right, electronics take two. So here is my new core assembly, and it covers the same features as the previous one, but with all new flavors. So our new flavor of processor is going to be the Arduino MKR0, which is a nice, simple 32-bit microcontroller, and it's a fantastic, simple dev board, but it does not have a built-in inertial measurement unit. So I'm going to use the BNO55 from Bosch, and this is going to be our new IMU. And this is great because the Bosch sensor does the sensor fusion in-house, in-chip. So we don't have to waste processing time doing any sort of calculations on our main controller, which the Arduino Nano would have to do. So more expensive, but more reliable and just really fantastic little IMU. Now you'll notice that this is mounted to a Raspberry Pi prototyping plate, and that's because I'm also switching over to a motor driver that was meant for a Raspberry Pi, but there's no reason to use a Raspberry Pi for this kind of project, especially for something that's real-time and fast. So I'm just using this as a motor driver. Now this is a dual motor driver, so I'm not using two motors, just the one, but if I upgrade in the future, I can just pop this little module out and put it somewhere else, which is kind of nice. And this will drive our motor, and it's also got a nice built-in 5-volt regulator so that I can power everything nice and readily. But as you can see, it's very, very little going on electrically, and this will be the heart of our unit, the heart of our balancing robot. And here is the completed design. It is not a remarkable innovation of balancing robot design, but it will get the job done. And I've added one feature that I haven't seen on other builds that hopefully makes sense, and maybe you can incorporate into your build too. So I've got my battery mounted here, sandwiched between two pieces of plywood, and this gives me a nice high center of mass for added stability. This is elevated on two threaded rods, which just thread into the 3D printed base. And the base is, of course, the core of the structure. We've got an aluminum L bracket for mounting the motor, our pulleys, our timing belt, and our wheel. Now, yes, there are two treads on this, but it's still a mono wheel. My goal for this is just to focus on maintaining a single axis and balancing, of course, across that single axis, and not worry about differential steering or anything like that. So this just gives it a really wide stance, so I don't have to worry about it tilting left and right. I'm only interested in pitching forward and back. Now, one thing I did add, which I don't see in other builds, is this larger threaded rod here, because I can't precisely control how even that center of mass is forward to back. So to allow for fine adjustment, I've got this threaded rod so I can add more mass to the front, add more mass to the back, whatever. And this is reasonable without any extra weights. So I can just thread this through the robot itself to finally adjust that forward to backward mass distribution. But other than that, we've just got our carrier plate for the electronics, and that's it. There's really not a whole lot to a balancing robot, but let's dig a little bit deeper.
Are you an engineer, electronics hobbyist, or maker? Join the Element 14 community, where you can learn about new products and technologies, see cool projects, and connect directly with the people that make the products and engineers that use them. Join now!
Okay, so here we are with the completed balancing robot. And as you can still see, it remains remarkably simple. Now I've removed the mass distribution rod, aka this piece of 1/4-20 threaded rod, so that I can lay flat and we can run through how everything is connected. So I always like to start with power, so let's work our way through the circuit. Up top, we've got our lithium-ion battery. So this is a 3-cell battery, and fully charged, this will give us 12.6 volts. This comes down to our XT60 connector, which has a female receptacle right here. This connects directly to our motor driver. Now, this particular motor driver takes our higher voltage and also has an integrated switching step-down regulator for 5 volts, because this is meant to attach to a Raspberry Pi. So that gives us a nice 5-volt source for flipping around our MKR0. And of course, the MKR0 runs at a 3.3 volt VCC, and that also connects to our, what's this, the inertial measurement unit. I know it, I've said it plenty of times, how could I forget? So this provides 3.3 volts for that, and this is also just connected via the I2C bus onto our MKR0. Now this is all mounted on a Pi prototyping PCB, just to keep everything nice and tidy, but there's remarkably little wiring. We've just got our connections to the sensor, and our connections for power, and our connections to the motor. So of course we've got these screw terminals right here, and this connects to the leads of our DC gear motor. And that's it. This is a very elegant build, and like most balancing robots, you don't need a whole lot to get started. So let's go ahead and turn this on and test it out. So we're going to talk about the basic theory that explains what's happening to the robot and how it should respond. Now, there are far better videos out there that explain PID control theory and how to tune your controller. So I'm gonna have those links, and I'm only gonna go into the very basics of the proportional aspect of it, because you don't need to have a deep understanding of physics to really grok it and see how the robot should respond. And I am very much a novice at this, so I shouldn't be the one to teach you about PID controllers, and you should go watch those videos instead. All right, let's get into how this is actually going to be. So we've got our nice robot here, and it is built and ready to go, and it is 90 degrees vertical. But chances are it's not perfectly balanced, which means that it's going to tilt one way or the other. And gravity is constantly bringing us down, man. So in order to counteract gravity, we need to apply a torque right here at our pivot point so that we can accelerate in the other direction. Now, depending on how far we're tilted, which, you know, if you want to be at 90 degrees, you'd say, hey, 80 degrees, that's a problem. We've got an error here, so this is that angular error that we want to compensate for. But if it's only, you know, a few degrees, we don't need to apply maximum throttle to our motor. That's too much. We just want to proportionally respond to how much error there is in our angular position. And in this case, I'm going to say this is the pitch of the robot, because that would be facing forward. So if we're tilted a little bit, respond with the smaller torque. If we're tilted a lot, respond with an even larger torque. And if we're completely vertical or flat, horizontal, then just turn off for right now because it can't recover from this. So here's a couple things that will happen. First, if the robot is tilting and doesn't apply enough torque, just a little bit, if there's not enough of a proportional response, it might push back a little bit, but it's still going to accelerate and eventually fall. So that one, not as common. Chances are what you'll do first, which is what I did first, is you will respond too forcefully. Now, if we're tilting and we apply too much torque, then chances are we're not just going to go vertical, we're going to go backwards. And now we've got gravity and our added momentum from accelerating backwards that we need to overcome, which stinks. So the robot should, hopefully, be able to respond. So if it's already at max throttle, if it's already saturated, then it won't be able to, because it's given it all she's got, Captain, and she can't respond any more forcefully, so it's just going to fall down. But if you still have some force to spare, then it will move back. Now, chances are, if you overshot once, you're going to overshoot again. So you're going to go forward and backward and forward and backward. And chances are that's probably going to cause some instability and it'll probably fall. Or you'll just have a really jittery robot, which, no one wants a jittery robot. I mean, I love jittery robots, but I want a perfectly well-balanced robot. So what we want to happen is when we've got that error, we respond quickly so we can beat gravity, but we don't want to shoot ourselves in the foot and over-accelerate in the other direction. So very quickly respond proportionally as quickly as possible and get back to vertical and stay there. And that's the gist of the proportional aspect of the PID controller. Once again, go watch those better videos that explain it, but that is the general theory of how this robot is going to react to the forces of reality. And so concludes step 1 of my saga towards building a Securitron. This little prototype was actually really handy for me to learn some of the dynamics and the basics of the control theory that go into a balancing robot. You can read all the articles you want, but until you actually build something physical, that's when you're really going to grasp it, or at least that's when I actually soaked a lot of this in. And there are still a lot of things that could improve. There's still a fair amount of backlash in the system, which means no matter how responsive this is, if there's mechanical backlash, it's always going to be just a little bit unstable. The rigidity of the system matters a lot, so there are times when certain screws were just a little bit loose, and then wobbliness also adds to the instability. But these are all the things that I wanted to learn, and I feel confident that I can build a bigger and better balancing robot. Have you ever built a balancing robot? Or what would you do to make your own balancing robot better? Let us know at the Element 14 community at element14.com/presents. I'll see you guys next time.